the stream. Everything should be open except the iClicker software, which was open and now is gone forever. So today we are going to continue and actually get into the content. We kind of touched on units last time, but we're going to get into more of the nitty-gritty there, and hopefully, fingers crossed, we'll get into vectors. My hope is that we'll actually finish vectors sometime maybe in the middle of class Friday, and then hopefully get into 1D kinematics starting halfway through class Friday, because we don't have class Monday, which means we lose a day, which means we're kind of going to be playing a tiny bit of catch-up. Hey, good, nice, you found it, good.
Right, thank you.
Yeah, no problem. All right, so I didn't upload any slides because I hadn't done any writing yet. That will change today. So after today, I'm going to do some writing on these, and therefore I will post the updated ones with the writing. So you all didn't get to see me do that, but it will happen. So we talked about units. I said, what is 3? 3 is an idea. 3 means nothing until I put a unit after it. Every single measurement that you can take will have an associated unit with it. If you measure distance, the unit will be meters. If you measure time, the unit will be second. I will introduce, every time I introduce a variable, there will be a whole slide dedicated to it, and it'll tell you what unit goes with it, what the base unit is, all that jazz. So right now I'm kind of mentioning some off the cuff. Those will actually come up next week. Distance, time, acceleration, velocity, those are some of the first ones. But for now, just a grand sweeping thing, units, everything has one for the most part. All right? The metric system is the best system. Here in the US, we use the imperial system. There's only 3 countries in the world that use our system of feet, miles. You got the US, you got Myanmar, which if you know where that's at on a map, your geography is better than me. And then I believe Liberia is the 3rd country that uses feet, miles, that kind of pounds. Every other country in the world uses the metric system because it's just easier. It's so much better. An easy way to prove that to you all is, let's see, actually am I asking that in the next slide? Nope. Easy example of that is how many inches are in a mile?
5280.
So that being how many feet are in a mile? Then you get the pleasure of multiplying that by 12. If you can do that in your head, you're better than me. At least like super quickly and accurately. 5,280 times 12 is awful. That's just not a fun thing to do. If I say how many millimeters are in a kilometer, I just move the decimal place 6 times and I'm done. It's awesome. It's so much better. Everything is in base units of 10. So everything we do in this class is going to be in the metric system. That's what every scientist in the world uses. Engineering, you are on the border. If you are an engineer, that's a career path you go. You will be working in both of them, depending on what job you're in. So that's a fun time. Sometimes you'll be working in feet, sometimes you'll be working in meter. Depends who you're working with. If you're working with other countries, if your parent company's over in Europe, it's just a bit messy. The reason why the US hasn't switched, in my mind, I haven't looked this up, but if I had to guess, it'd be expensive. Just literally think of replacing every single miles per hour sign with kilometers per hour sign, and the cost that would incur. It's just kind of, I don't even know how we would do it at this point without incurring a massive cost, and I suppose it's not worth it, but it's a pain. All right, so these 3, we're going to see a lot. Meters, kilograms, seconds. These are something, again, we're going to talk about math, we're going to talk about distance, we're going to talk about time more in detail. But for now, just kind of quickly, length is measured in meters, mass is measured in kilograms, time is measured in seconds. Kilograms is the only base unit that has like a prefix in front of it because someone decided at some point that's how it's going to be. The rest of them, no prefix. And we're going to get lots of practice for these prefixes. I mentioned them last class. You do not need to know all of these. Remember, you do not need to have things memorized in physics. And to that end, there is something I forgot to tell you all about the tests. So on the test, I will give you a formula sheet, all the formulas that you'll possibly need. But what I will also do for you is I will let you use a 5x8 note card and write anything you want on the front and back of that note card. I will provide those note cards a week in advance. I'll just have a stack of them. They're not too expensive, but it's not like you all can just buy a single 5x8 note card. So instead of you ending up with 100 of them that you won't know what to do with, I'll buy 100, 200 of them, have them up to you, grab one. You can put anything you want on that note card. Anything in sheet on the test, so I wouldn't even tell you, hey, here's the formula sheet, so I'll show you what I'm going to give you on the test. This may be something you may want to put, is these conversions from centimeters to meters or millimeters to meters. If that's something that you're afraid you'll forget, you can put it on there. Physics is not about memorization. If it was, I wouldn't be in it. I hate them. I say hate. I'm just terrible at memorizing. Really bad at it. And the beautiful thing with physics, you don't have to have anything memorized. I guess you need to know that meters measures distance and stuff like that. But it's so small, I don't even count it. So to that end, you can put whatever you want on that note card. If there's a problem that you're really scared of, you can work out that whole problem. The reality is, when it comes to tests, the challenge is recognizing what type of problem it is and how to set it up. Nothing on your note card is magically going to kind of reveal that to you. Maybe you hints and nudges, and that's what I want it for. It's going to be one of those, either you know how to solve this problem or you don't. And to that end, I'm not worried about what you put on the note card. It's not going to necessarily, it's not really cheating, but I do limit it so that everyone has kind of a fair, the playing field is equal. I care about the process. That's what physics, engineering, all that. I am teaching you all how to think critically within the context of the rules of the universe. So, anyway, all that to say, note cards are great. So, first clicker question. How exciting. So here's the table. If you have that pulled up, great. If not, feel free to look it up on your phone or something like that. You know what? Here, let's just copy and paste that over. Why not? Bam! What is 38 kilometers in meters? So this is a good example of what the clicker questions are going to look like. I will open them up. They will always be multiple choice. A, B, C, D. Every now and then there'll be E. If you're like, what class code thingy? It's AA. It's always AA. There's no other class in here that I expect interference from. So your frequency that your thing should be on is AA. I will open the clicker question. It will generally ask me this thing. So if you have the app version of this, it will send a screenshot of the question of my screen to your phone, so you'll get to see the question on there as well. So if you're at home or whatever, it'll do that for you. If you're here, it'll do that for you. And now you have some amount of time. That amount of time, so it counts up because I just kind of base it on this problem. I'll give you like 30 seconds. It's a quick problem, 30 seconds. I make up the time depending on the complexity of the problem. So, what is 38 kilometers in meter? Answer A is 38 times 10 to the 3. Answer B is 38e3. Answer C is 38,000. And answer D is 3.8 times 10 to the 4 meters. What is kilometers to meters? And then at this point, what I will be doing is I can see the responses on here, which is real handy for me. Kind of gives me a sense of how many people are responding. Generally, ideally, as the weeks go on, I will have an idea of how many clicker questions there are. And at that point, I also use that to gauge how long to wait and all that kind of jazz. So don't rush these problems. If I say you have 30 seconds, don't feel like you need to rush. If I see that half the class hasn't responded, I will say, hey, you have 20 more seconds or something. I'll make a statement with that. So, again, this is just a good example of that. We'll go ahead for 5 more seconds. So 5, 4, 3, 2, 1. And we close it, and then we look at the answers, and then I tell you, every single answer was right. Every single one of these is a conversion for 38 kilometers to meters. Every single one of these numbers is the same number, just written 4 different ways. Now, that's important because on the quizzes that are each week, or even on the test, they're multiple choice. So if your answer doesn't necessarily look identical to one of the ones that's written, it may still be the same number. So that's where we have to get used to the different ways of notating things. So just a reminder to you all, just to kind of unpack what the heck I'm saying here. So ultimately, 38 kilometers to meters, if we look at our little table here, it says that to convert to kilos, we just add an e to the 3 to it. A times 10 to the 3. In fact, let's make it look like the table. Times 10 to the 3. But I told you all that I use the e instead, because that's how your calculator does it. So that's the same. But then we also need to remember what the heck scientific notation means. It means you move the decimal place 1, 2, 3 times to the right, 38,000. Well, this last one, if I actually just wrote out that number, it's 3.8, so I'm going to times 10 to the 4, so I move the decimal place 1, 2, 3, 4, And look at that, it's the same number every single time. Again, this is just kind of an exercise in different ways to write big numbers or small numbers alongside converting units. All right, so great, metric units, super easy to convert. You just multiply it by whatever that exponential multiplier given in this table. Honestly, once you do this enough time, like, y'all will have this memorized lickety-split because you'll do it so many times, I'll trick you into memorizing it. But you do have to be careful and make sure you do it. All right, next one, how many milliseconds are in a minute? I will tell you all that minutes don't follow the nice metric rules, but everyone in the world uses them, so at least we're all in it together. How many milliseconds are in a minute? And let's see, did I make a boo-boo here? Nope, we're good. I try to double check my work, but I can promise you all, I will make mistakes up here. Promise you all that. Because I'm a human being, and no matter how much I double, triple check these things, that's just going to happen. So the takeaway from that is if you get 100 on a test, that is very hard to do. Getting 100% on any test in any class you ever take, it's hard to do. It's hard to be perfect. In fact, being completely perfect is impossible. But getting an A is definitely doable. An A is, hey, I made a few mistakes here and there. All right, give you all 10 more seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. Pachow. All right, so let's go ahead and solve this problem out. So, to get milliseconds in a minute, we have to first convert to seconds. Yeah?
I don't know if this was universal, but I did see the question 2 just closed out on me.
Question 2.
It probably was just my phone.
Did it just close?
No, it closed before.
Oh, weird. Okay, yeah, it shouldn't do that, but definitely let me know if it keeps doing that. So first we have to say how many seconds are in a minute, and then we can start doing all the metric prefixes. So there's 60 seconds in a minute. And then we look at our little thing here, and we see that there is 1,000 milliseconds, or 1,000 millis in 1 second. There's 1,000 milliseconds in 1 minute, meaning I need to actually multiply this by times 10 to the 3, and this is where it gets a little tricky with this table. 1 millisecond is 1 times 10 to the minus 3. So if I was going from milliseconds to seconds, any of these multipliers here are to go from whatever it is to the base unit. If you're doing the opposite, then you need to change this sign. So in our case, instead of multiplying by 10 to the minus 3, I need to multiply by 10 to the positive 3. Because I'm not going from milliseconds to seconds, I'm going from seconds to milliseconds. I'm doing the opposite case here. Now, if you're like, how am I going to remember that? There's a really easy way to determine whether or not you're doing it correctly. So, just to show you all what I mean, it's 60 times 10 to the 3 milliseconds. And you're like, that's not one of the answers. It is. That's the exact same number as this one. 6e to the 4 is the exact same as 60e to the 3. You just move the decimal place 1 over, and it's that one. Feel free to check that out for yourself. Now, I just told you all and just to write out this number, it's 60,000 milliseconds. Here's how you can check if you converted your units right. This is going to sound stupid. You just think about it for a second. That sounds really stupid and general and obvious. Is there a lot of milliseconds in a second, or is there little, very, very few milliseconds in a second? That's the way to think through your answers when you're converting units. That's how you can catch to make certain you're not going the wrong direction. There's a lot of milliseconds in a second. There's 1,000 milliseconds in a second. So I should get a really big number. There's a lot of milliseconds in a minute. If instead you went the wrong way and you put 60e to the minus 3, which wasn't even one of the options, but just say I did put that and you actually put that, just think about the answer for a second. That's 0.060 milliseconds in a minute. That means there is less than 1 milliseconds in a minute, which is not true. It's kind of like saying there is less centimeters in a meter. So, when you're converting units, when you're doing a quiz, when you're doing a test, and you're doing these unit conversions, every now and then just pause and think, did I go the right direction? It sounds silly, it sounds stupid, but I can almost guarantee you that every single one of you will make a unit conversion error at some point. Because I have made a heck of a lot of unit conversion errors in my life. A lot of them. I've done a lot of physics problems. Every time you do a unit conversion problem is a time that you can make a mistake. If you make a mistake 1 in 1,000 times, well, you're going to probably answer. In this class, you won't answer 1,000 times, but you will at some point. All right. Great. All right, problem solving number 1. And I didn't do a good job of this here, but something I want to point out. I am fairly confident almost every single time I do one of these problem sets, one of these worked out problems that have a few more steps than a clicker question will warrant. Did I do it here? There it is. This is number 4 in the problem set. So almost every time I work out a problem in front of you all, it will be one of those problem set problems. So that's just good for you all to know if you're like, oh my gosh, well, 12 questions isn't that many. But if you're ever intimidated by how many, I will generally solve between 2 to 4 of those problems out of the 12 in front of you. So anywho, that was number 4. Number 4, units and vectors. Number 4. I even usually tell you which problem it is. That's why I was a little uncertain here. All right, so we're going to work this out. A car is traveling at a speed of 120 kilometers per hour. What is its speed in meters per second? We don't even need to know what the word speed means. All we need to know is how to convert units. So we need to go from 120 kilometers per hour all the way over to what it is in meters per second, and we are going to do that piece by piece. First thing we recognize is kilometers is not meters, so we need to convert that. So we do the same thing we did last time. We look at our little table thing and we say, oh, there's 1,000 kilometers in a mile, aka I need to multiply this by 10 to the 3. So great, I've got my thing in meters per hour now. Top part's done. Next, I need to convert that hours into seconds. So to do that, and again, this is where it's handy. If you're like, oh, do I divide by 60? We say, okay, there's 60 minutes in an hour, and then there's 60 seconds in a minute. When you're looking at this, you're like, do I divide by 60? Do I multiply by 60? You just think through what makes sense giving this. If I'm going 120 times 10 to the 3, who cares? Let's just say it's 5. 5 meters per hour. So every hour, this is how many meters I'm traveling. So does that mean I'm traveling more distance in seconds or less distance? Every second, am I traveling a bigger distance than that or a smaller distance than that? Well, if I travel this many meters in an hour, I should be traveling a lot less meters every second. Because the second's much shorter. So every second, I'm traveling way less. So that kind of tells you that I'm going to be dividing by 60. There's 60 hours, or 60 minutes in an hour. So we're slowly but surely getting our way here. And mathematically, you can also see this. There is 60 minutes. So we need to get rid of this hours. We're going to do that by dividing by 60 minutes per hour. So mathematically, we get to see it, but you can also just kind of logic through it. I honestly do the logic case. I don't do the unit thing. I just say, oh, if I'm going in seconds, it should be smaller. So I should divide by 60 instead of multiply by 60. Do whatever works best for you. All right, so we're going to divide by 60. The hours are going to cancel. We have 120 divided by 120, e to the 3. Thankfully, I can do this math in my head, not because I'm talented, but because 120 divided by 60 is easy. Great, we got meters per minute. Almost there. We're getting there. Now we got to go from minutes to seconds. We're going to do that same thing. We know it should get smaller, so we're going to divide by 60 seconds per minute. That's going to get rid of that minutes. That's going to replace it with a seconds. In this one, we're going to get 1 over 3. That's not a very nice number. And to make certain, so at this point, this may seem stupid, but I'm going to use a calculator for this. Why? Because I don't want to make a silly mistake in front of you all where I'm off by a decimal place, and this is the kind of thing where you will do that. Where it'll happen, where you're like, oh, this is so easy. It's 0.33 times 10 to the 3 or whatever, and you may just end up making a silly mistake. If you plug it in your calculator will never make a mistake if you plugged it in correctly. So it may seem stupid to plug simple math in, but what's more stupid is getting a problem wrong when you know how to do it. So, let your calculator bear the brunt of the cognitive thinking. Let your brain figure out how to solve the problem, and then let your calculator do the solving for you. It's just the smart thing to do. You'll see what I mean. So, for example, it even gave me, look at that, 333 meters per second. If I had wanted to keep it as before, that would have been 0.33 times 10 to the 3, so it confirms what I thought. And we check our answer to make certain it makes sense. That is a key, what I just said there is a key step you should do in every single problem. When you get a final answer, the beautiful thing with physics, it should make sense. It's the real world. If you're measuring the velocity of a car and you get that car is going 1,000 miles per hour, that's not realistic. Something went wrong. Yeah?
I might have missed something, but it's 120 divided by 60. Why did that turn to 20? Shouldn't it be 2?
When you did 120 divided by 60, see? Look at that. I told you all. It happened. I made a stupid math mistake. Why? Because it just happens. Yeah, so 120 divided by 6, yeah, so it's going to be 120 by 60. It wasn't 20, it was 2. Case in point, y'all, it may seem like that was a really stupid mistake for me to make, and I'm going to make a lot of them, and you're going to make a lot of them. It's going to happen. So, don't worry. I have no shame in this, and so hopefully you all will also have no shame in this as well. We just move that decimal place over 1. And we get 0.033 if we want to do that there. There you go. Please call me out if I make a mistake like that, because I can almost guarantee, again, it'll happen. Making a mistake doesn't mean, when you make a mistake like this, it just means you're human. It's going to happen. Anyway, moving onwards, there you go. So converting units, something very important. It's hit or miss. Let's just quickly peruse through these problems. So obviously in the first set, you're going to have to do that. But let's look at future sets. First problem here is in kilometers. So this is for 1D kinematics. You're going to have to convert that to meters. Second problem here, that one's in seconds are fine. Third problem has kilometers and minutes. You need your answers in meters per second. You're going to have to convert the units. This is going to happen on a lot of problems. The numbers I put, you may have to convert them. This one, kilometers per second, going to have to convert it. You're going to see this a lot because in the real world, when you measure something, sometimes you're going to measure it. If I'm measuring the distance from here to my house, I'm not going to do it in meters. If I was a scientist, I'd measure it probably in miles, because that's what people measured large distances in. So I'd have to convert that to kilometers, I'd have to convert that to meters. It is important to know how to convert units because you're going to have to do it in the real world. The thing you measure may not be in the base unit, and that's just how it goes. If you're measuring something really small, you're not going to measure it in meters. That's just ridiculous. Imagine taking a meter stick and trying to measure how many meters this pencil's width is. That's a weird thing to do. No one's going to measure this in meters. They're going to measure it in millimeters using some calipers. But if you had to do some math with that, you'd have to convert it to meters. So, just showing you all, why am I having you do all this unit conversion stuff? Because that's how the world works. And hot diggity dog, get into vectors. Units, pretty straightforward. You get lots of practice with that. Vectors is the meat of this week, and it's what we're going to spend the most time on. A whopping 15 or so slides on vectors with lots of practice and stuff like that. We are going to become BFFs with vectors. It'll be a love-hate relationship. But here they are, in all their glory. Vectors. There is some quantities in this world where not only does it matter how big the quantity is, it also matters what direction that quantity is going in. Easy example, if I told you all that I'm going to throw this pencil at 10 meters per second, okay, great, that's interesting. That tells you how fast it's going. Doesn't tell you if it's going to hit you in the head or not. The direction clearly matters then. If I told you I'm throwing it that way, then people in this direction should be concerned, and the rest of you know you're fine. Direction matters for certain things in physics. Those are the things with vectors. We have to take that into account. It's how the world works. It's a three-dimensional world. Some things have direction, some things don't. Your mass. There is no direction to your mass. How much stuff you're made of, there's no direction to that. You just have it. That's an example of a scalar. That's an example of something that doesn't have direction. You don't have to worry about it. The math is way easier. Why are some things have direction, some don't? Not my decision. It's how the world works. So, back to vectors though. They got a direction. They have an amount. This is how we represent them. We represent them with an arrow. How big the arrow is how large that value is. The direction it is, we will generally measure with an angle, most often with respect to the positive x-axis. But it could be given in any way. So this one I gave you here, this is the positive x-axis, and the angle is given with respect to that. But I could have totally given you a vector here, where it's this angle instead. That's with respect to the positive y-axis. It all depends on the problem. And so you have to be careful of that. All right. So, vector notation. You may or may not have seen this before. It's been a long time since I took Calc 1, so I'm actually going to get a quick check from you all. Have you all seen IJK notation? Some of you, yeah. Oh, yeah. You have seen, okay, great. So, okay, you have seen IJK notation. I honestly do not remember. It's been, oh my gosh. I graduated high school in 2011. Went to college the next year, took Calculus 1 in 2012. It's been 11 years. 12 years. 11 years. 11 years and so since I took Calc 1. So I don't quite remember what was covered in it. But great. If you've seen IJK notation, fantastic. If not, don't worry, we're going to cover it. This is the way we denote vectors in equation form. So you saw the visual form, arrow, angle. It'll usually have a number next to that arrow. If we write it in kind of math form, number form, we use this IJK notation. I is generally in the x direction, which we generally denote as left-right. X is generally left-right. Y is J hat is in the y direction. That's kind of in and out. And Z would be up-down. Depending on what you see, sometimes they kind of flip J and K. Sometimes they say Y is in the up-down and Z is in the in-out. For our class, it doesn't matter anyway. We're only going to work in 2 dimensions because all the benefit that you get from 2 dimensions, 3 dimensions, you don't get too much benefit from the extra complexity. Hence why I only put 2 dimensions here. So this says, whatever this measurement is, there's no units here, so this is just an idea. This hypothetical unit, let's just say it's distance. It's measured positive 8.66, so 8.66 meters that way, and 5 meters that way is how it would kind of pan out. So in the case of our class, because we're only working in 2 dimensions, let's call this the x-axis and the y-axis. That would mean if I drew this vector, so I'm going to dot these lines just to note that they're not my actual vector. That would mean I go 8.66 units to the right. Let's just hypothetically say that's here. And then I go up 5 units. 5 is a little bit less than 8.88, so the arrow would be something like that. More in the x direction, less in the y direction. This side down here measures 8.66. This side over here measures 5.00. And that's how we would draw our vector. Okay? We're going to get lots of practice with that. All right, and that's kind of what I just said as well. Look at me, consistency. We draw the vector by drawing a triangle. So we draw the bottom side. That's going to be our x. That is 8.66. So this is me just repeating what I said before. And then we go up 5. We're going to be big fans of triangles in this class, y'all. Vectors are all about triangles. I told you all about trigonometry, that you need that knowledge. This is why. Anytime you'll have these vectors, you're going to have the x component on the bottom. And you can almost view this thing. One way to view vectors is the x is almost like a shadow. So like if there's like a flashlight here, the shadow of this vector on the x-axis, that's the x component. And if you had a flashlight shining from this side, the shadow of this would be the y component. That's kind of one way to understand how these develop. I don't know. That was something that occurred to me at some point. I was like, oh, that's kind of nice. If that wasn't useful to you, throw it in the trash. All right, now we need to remember some trigonometry. So we got a triangle, we just saw it. This triangle had a side of 8.66 down here, 5.00 here. If I want to figure out the magnitude. How big is this third side? It's a triangle, right triangle, a squared plus b squared equals c squared. So we would say this side, this is also new notation, this magnitude of a. So a is the vector, the magnitude of it is how big it is. So these lines here are basically saying how big is the vector. Overall, this is a scalar quantity. Anytime you see this little arrow, vector. Anytime you see this little hat, vector. Anytime you see a little arrow or something, it's a vector. If there's no arrow, it's not a vector. So again, just little key facts here and there. So the magnitude of A is going to be, it's the hypotenuse, 8.66 squared plus 5 squared equals a number that my calculator will tell me. There's no way I'm trying to do this in my head. And pro tip to you all, what you're going to see me do a lot in this class is when I set up equations, I'm going to try to set up the equation such that I can literally plug the entire thing in my calculator in one go and then hit enter. The more times you have to plug stuff in your calculator, the more likely it is you're going to fat finger the wrong button and get the wrong answer. The other pro tip is whenever you type something in your calculator and get the final answer, double check that what you typed is what's on the board. Again, because you are going to hit the wrong button on your calculator at some point in this class and get the wrong answer. I'm sure you've done it. You've taken a lot of math classes, I'm sure it's happened to you. So, by writing down what to do, these are all just techniques to reduce the chance of making human error. We're all prone to it, because we're all humans. And we get 9.999997. We'll just go ahead and round that to 10.00 to 2 decimal places. This is another good opportunity to tell you something in physics. A rule, we don't use significant figures in physics. I'm hitting you all with a lot of just like random information, but it'll get repeated. Whenever you answer a problem in physics, I don't need 10 decimal places. I don't want 10 decimal places. A rule of thumb in physics, I don't know who decided this. I'm literally just basing this on my 9 years of taking physics classes, 2 or 3 decimal places. That's the rule of thumb. How many digits do you need to put? 2 or 3. You're going to notice every single answer I put, every single quiz, every single test, 2 or 3 decimal places. When you all take physics 2, hopefully you'll see that instructor does the exact same thing. We're not looking for crazy precision here. We're looking to see that you understand how to do the problem. 2 or 3 decimal places is good enough. I forget, it's either, I think NASA only uses, it's somewhere between 5 and 9 digits of pi when they do their calculations. They don't use pi to like the 50th digit. They only do it to like the 5th or 9th digit because that's good enough accuracy for what they need to do. 2 or 3 decimal places is good enough accuracy for what we need to do. All right. Oh, let's do that last part. I forgot to mention the last part. The angle. So we need the direction. We know how big the arrow is. We need to find the direction of it. We're going to use handy-dandy tangent. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. If we look at our handy-dandy triangle, that's the opposite. That's the adjacent. 5 is the opposite. 8.6 is the adjacent. So, and again, because you all are fairly capable with math, I am not going to write out quite all the math steps there. I just plugged in 5 is the opposite, 8.66 is the adjacent, and to get rid of the tan, you do tan inverse. This is something you're going to have to do. And the other thing you got to be careful of is what mode is your calculator in? Is it in radians? Is it in degrees? We will largely be working in degrees in this class, but every now and then you'll need to have it in radians. I will make certain you know beforehand when those cases occur. In this case, if I want the angle in degrees, if I give you a quiz and every answer is in degrees, that gives you an indication what it should be in. 30 degrees, 30.00 degrees. Boom, there you go. All right, so that's how you get the angle. We're pros at it, right? Well, I'll leave that for a few more seconds. All right. So what I would like for you all to do now, which of the following shows the vector negative 15.79 I hat plus 12.04 j hat? And I will remind you all that any clicker question I give you should generally be able to be done in less than a minute and a half. So that means that there is probably a trick to solving this that doesn't involve math. Now, this is also a good point to notice that every now and then, my PowerPoint does its best impersonation of the Christmas Story, does the Ghost of Christmas math problems. They like stick to here and I have to close the thing and reopen it. I have no idea why it does this, but every now and then if you're like, what the heck, why is that there? It shouldn't be. So I will have to close it and reopen it. What a joy. In fact, I need to save it first because all that precious writing I just did will be disappeared if not. And unfortunately, there is no way for me to freeze the screen up here, so you just have to bear with me. But it's going to happen. No idea why. Happens in my high school classes. Happens with this. I don't know if it's my computer. I don't know if it's PowerPoint. But it just results in a little bit of a delay. And we're back. It's the only way to solve. There you go. All right, so with that little snafu done, y'all have 15 more seconds. There is no math required here. And we'll go to 25. We'll make this much bigger because I know that is... In general, I try to make things as readable as possible. I did a terrible job here. All right, so 5, 4, 3, 2, 1, 0. So, you are more than welcome to have done the math. Square root of 15.79 squared was 12.04 squared and gotten a magnitude and found the one that did that. Or, we can think about what this vector, what's going on here. We have a negative in our x direction. So we immediately look at the ones that are even an option. This one, that's in the positive x direction. That's ruled out. This one, positive x direction. That's ruled out. So we have this one, that's in the positive x direction. That's ruled out. We got 2 choices left. Our y is in the positive direction, 12.04. That is a positive. This one's pointed down. That's in the negative direction. Ta-da, our answer is D. Now, if we do the math, fingers crossed, if this is wrong, it's OpenStack's fault, not mine. Though I guess I could have double checked it. 15.79 squared plus 12.04 squared comes out to 19.86. We'll round that to 20 and call it good. They rounded a bit more generously than I probably would have, but that's close enough. So there you go. That was just an exercise in making sure we understand how vectors are. We'll get into this one next time. We're at 5. Oh, no, we got time. I keep forgetting. All right, great. So now we're going to do the opposite. So we figured out if we have the 2 sides, x and y, how do we get the magnitude? How do we get the whole vector? And how do we get the angle? Now we're going to do the opposite. And here's where that whole shadow thing I mentioned comes from. To make this triangle, we basically do the x component, we go on down, and we say, there's our x component. And then our y component, it's kind of already here, bada bing, bada boom. There's our x component. We will call this a y. We will call this a x. That is a notation you'll see. Those are subscripts. So to make it really clear, I'm going to make it really big. I put those little letters down to the right of it. That's a very common notation that you're going to see me do in this class. Whenever we're talking about something in the x or y component, we'll put whatever the variable is, and we'll put a tiny little y next to it, or a little tiny x next to it, depending on which one it is. If it's just the vector, it just gets the vector. And these are both vectors, so I'm actually going to put those little arrows over it to denote that as well. If you really like, you can make it a full arrow, but for the sake of convenience, I just do that. All right, it's a right triangle. I have the hypotenuse. I have the angle. Hopefully your trig skills, you're feeling pretty good about how to get it. It's going to be SOHCAHTOA. Now, which one do you use depends upon what angle I give you. So I'll show you how to do this one, and then I'm going to tell you all to be careful because a lot of people in physics get into a specific habit that isn't always true. All right, so if we look at this triangle, it's kind of written out for here, so it'll save me a little bit of time. So if we have the hypotenuse, this is the opposite side. The y component is the opposite side, so we're going to use cosine. Nope. We're going to use sine. So sine of theta equals ay over a. Rearranging that, we get ay equals a sine of theta. If we want the x component, cosine equals adjacent over hypotenuse, ax over a. Rearrange that, you get ax equals a cosine of theta. What I do not want you all to see here is that the x component is always a cosine theta. What I do not want you to do is to say that the y component is always multiplied, the hypotenuse times sine of theta. It is not always, the x component is not always the cosine. The y component is not always the sine. The immediate question that may come to mind is, when is it not? What if instead of giving you this angle, I gave you this angle instead? Now it's flipped. If I gave you the top angle instead, now the x component is the opposite side. So it'll be a sine theta. Now the y component is the adjacent side, so it's a cosine theta. Make certain you're careful with that. A lot of engineers, physicists get into the habit because you're going to often see, I will often give you this angle. It will very often, probably 90% of the time, be x component's cosine theta, y component's sine of theta. But not always. Not always. Don't get into the rut of it's always cosine, it's always sine. It won't be. And that would be very sad to make that mistake. I can guarantee you there will be problems where that'll come up. And just make certain you're thinking through what you're doing when you're getting those components. And that you're not just saying, oh, x is cosine, y is sine every single time, now and forever, to the end of time. All right. And then you write it as such. The x component goes right next to the I, the y component goes right next to the j. Ta-da, we went backwards. Look at us go. All right. And because this is so important, that's going to be the first few problems in your problem set, is literally just So after units, a lot of it is just, hey, here's a bunch of examples, write the vector notation. And then the next one, we're going to get into adding vectors. We won't get to that this class, but you'll get more practice for that as well. All right, so write down the following vector and vector components. So this is one of those this is one of those pieces. I think I asked you for like 5 different ones. So we have our vector here, C. The first thing you want to do, draw that picture. We have our x component here. We have our y component here. If you all remember the problem-solving process, the first thing you want to do is draw a picture. I kind of gave part of the picture, but now I've added to it to make it a little easier. Ta-da, there's my triangle. Now, one of the things when you build this triangle is I also want to add arrows to these. I want to add arrows to these because I actually have to add the sign, positive or negative, based on the picture, not based on the math. You'll see what I mean as we solve this. So all you do is you look at this and you say, is it going more to the right or more to the left? It's going to the right. So our x component should be pointing to the right. I look at it and say, is it going more up or is it going more down? It's going more down. So I draw that arrow down. It is very important that you have the direction of these. Again, when we solve this, as we solve this problem, you're going to see why. If you do not put these arrows in the right direction, if you just do the math, one of your answers will be wrong. So, C, C is 12. I'm going to go through the problem-solving process. You do not have to do this in every single problem, but I just want to show you all that this is useful for almost every single problem we do. First step, what's given? C is 12, theta is 60. Magnitude of C is 12. Second step, what are we solving for? Well, we want to write the vector in terms of C, so we want C in terms of CXI hat plus CYJ hat, aka I want the CX and CY. Step 3, what equations am I going to use? Well, CY is going to be the hypotenuse times cosine. Nope, my bad. Again, I was double checking it. Sine, because it is the opposite side, so we showed that in the last one. Sine equals opposite over adjacent, rearrange it, you'll see that. Again, I am not going to, if this was a non-engineering class, I would actually write a lot more steps here. I would write sine equals opposite over hypotenuse, and then I would rearrange it. But because you all are engineering, because you've gone through Calc 1, I'm going to expect a little bit more from you all on that. But at any point, if I skip a step and you're like, how did that happen? Ask me. I want you to ask me if at any point I skipped a step and you're like, what the heck happened there? Pause me. I'm happy to answer it. I can almost guarantee you 10 other people will have the same question. Cx is going to be C cosine of theta because it is the adjacent side. And step 4, plug and chug. This is the easiest step because you've done all the hard work. The hard work is setting it up. So that's going to be sine of 60, which equals a number, 10.39. Cx equals 12 times cosine of 60 equals 6. Now, here is where our picture becomes very important. If I put the answer as this, 6I hat plus 10.39 J hat, it's wrong. I'm going to give you all a few seconds to figure out what's wrong about that answer. You don't need to say it or anything, just I want to give you all some time to think. The key to figuring out why this is the wrong answer is we just need to check if this makes sense. According to this, my x is positive. That's correct. It's pointing to the right. Right is positive, so that's good. Right is positive, left is negative, up is positive, down is negative. So my x is pointing to the right, so we're good there. According to this answer, my y should be positive. It's not. This is where I was telling you all the importance of a picture. The math doesn't tell you that the y direction is negative. The picture does. Now, the math could have told you that if you had put this angle as negative 60 degrees. Then it actually would have given you a negative number. You would have had to have made that distinction. But personally, I find it more easy to use the picture to decide when it's positive and negative. Just do the math, assume where everything will come out positive in terms of when you get these vectors, and then assign the positive and negatives after. If it's to the right, it's positive. If it's to the left, it's negative. If it's up, it's positive. If it's down, it's negative. I find that to be way more consistent personally. But if you so prefer, you could have made this negative 60, but then you get into the whole when is it a positive angle, when is it a negative angle, and that gets really funky and that has a bunch of rules that's not worth the time and energy in my opinion. So, draw a picture, very, very important. If you're doing a problem with forces and you know the object should move to the right and you get an answer where the object's moving to the left, something's wrong. Pictures will help you understand whether or not your answer makes sense. And here we can kind of check that and see that. All right, so we got 1 minute. I'm not going to get into adding vectors visually because I cannot. 1 minute's not enough to really get too much. But next class, that's what we're going to do. We're going to take vectors and learn how to add them visually and mathematically. And that'll be the last thing I need to teach you regarding vectors. So we will very likely be able to get to 1D kinematics and start getting into that a little bit early, which will be good because I won't see you Monday. It'll be so sad, but at least you'll have stuff to think about. If you have any questions, feel free to come on down. And again, I'll post this clicker score so you can see